Hi, I'm Max Majireck, a professor of chemistry at Hamilton College in New York. And in this course, we're going to talk about the chemical bond and the basics of bonding in organic chemistry. It's one of the most fundamental topics, and you'll build off of this knowledge throughout the course. So take, for example, this molecule, caffeine. This is my favorite organic molecule. I have it every morning, especially this morning at 5 a.m. after my daughter woke me up to wish me a good morning. This molecule got me through it. But more than just an appreciation of a molecule like caffeine, what I hope that you'll get after this first series of mini lectures is an appreciation for the chemical bonds that make up molecules like caffeine. So we're going to ask some fundamental questions. What is a bond? Are they static, like this model implies, or are they dynamic? In fact, they're dynamic. They rotate, they spin, and you'll be able to analyze things like that by the end of this. Also, we'll discuss what are they made of. We'll talk about orbitals, hybridization, and how that can impact things like the geometry of this molecule by the end of this course. And then that's foundational material that you'll build off of throughout organic chemistry. So without further ado, let's get into the nature of the bond itself. The first question is, what is a bond? And a bond is, as I already mentioned, not something that is a static line between two atoms, but it's actually a dynamic, attractive force. And in fact, in the simple terms, you could describe a bond as simply two or more nuclei that are held together by some attractive force. There's a law that helps us describe this called Coulomb's law, and it's a simplified view of bonds. So let me explain what this equation on the left here means. In this equation, I have it written out on the right in plain English. It's a force is equal to some constant. That constant is dependent on which atoms you're talking about, times a negative charge times a positive charge measured in a unit called coulombs. And that force is dependent on the distance between those charges squared. So if you plot that, if you take two atoms that I have illustrated here as blue and red, and you bring those atoms together, you'll get an energy plot that looks like this. We have potential energy on the y-axis, and interatomic distance, the distance between those atoms, on the x-axis. At first, these two molecules, or two atoms, would be too far apart, so there would be no bond present. But as they begin to get closer, those two atoms could begin to form a weakly attractive interaction. So we might even call this a weak bond. But whenever we're talking about a bond in organic chemistry, we're talking about something a little bit more specific. And that is the point at which these two atoms, or atoms in a molecule, are close enough together that the bonding potential is maximized. So the attractive forces are outweighing the repulsive forces. And this distance is what we call the bond length. So when a chemist refers to a bond, typically that's what they mean, is that average distance between the two nuclei. But of course, if you bring them closer and closer and closer together, the electrons are going to begin to repel, and the nuclei, the positive charges, are going to begin to repel. So this ideal distance of the bond length is typically where the molecule stays. But if you bring them too close together, the repulsive forces will make the potential energy shoot up, and that's an unstable configuration to be in. But getting back to this bond, if you imagine what's happening is this bond is sitting at this average bond length distance, but it can go back and forth a little bit in this energy valley. So the bond itself is not fixed. It's not like this model kit that I showed in the introduction, but it's actually dynamic. Bonds vibrate. Okay, so why does it matter that bonds are not static and that they vibrate and rotate and so forth? Well, that's a feature of a bond that is built upon throughout organic chemistry. I thought it would be fun and interesting to just give you a preview of some of the things that are based on bond dynamics. If you take a full organic chemistry course, one of the topics that you typically encounter is infrared spectroscopy. That's this graph shown here on the left. And what you can do is certain bonds vibrate at specific frequencies in the infrared spectrum. So you can measure their infrared absorption and make a diagnosis. This is a technique that's used in forensic science, for example. So this bond, this carbon-oxygen double bond, because it vibrates, that can be detected in the infrared spectrum by that peak that I pointed to. Another topic is conformational analysis based on bond rotations. And if you go through a module on conformational analysis, you'll appreciate that bonds can rotate, and in fact, this can change their energies and hence their reactivity. But throughout the course, including this series of mini lectures, we'll appreciate things like bond lengths, which we just defined. And this has an impact on their strength, something called their polarity, which we'll discuss, and also their reactivity. Let's get back to the topic at hand, the bond itself. In organic chemistry, there are two general types of bonds that we encounter. Now, there are actually more than two types of bonds, to be sure, but in organic chemistry, we encounter primarily a bond which is called a covalent bond and one which is called an ionic bond. But suppose you have two atoms, atom A and atom B, and you're going to form a bond in between those two atoms. If their electronegativities are substantially different, then the atom, which has a higher electronegativity, is going to steal an electron from the other. In other words, an ionic bond is unequal sharing of electrons that creates a positive and a negative charge, like this general example shown over here. A real example that you've likely encountered, especially if you've had a chemistry lab before, is sodium hydroxide. In sodium hydroxide, the electronegativity difference between sodium and oxygen is substantial. And oxygen is much more electronegative, so it forms an ionic bond with sodium, which takes on a positive charge, and the bond itself is actually just an electrostatic interaction between the positive and the negative charge. Now, in a covalent bond, if atom A and B have the same or similar electronegativities, they will share their electrons. They'll combine to form an orbital that has both electrons within that same orbital. And in this configuration of the covalent bond, you have attractive interactions between the electrons and the nuclei within that orbital, in addition to repulsive interactions between the two like electrons or the two like positively charged nuclei. But that attractive force is maximized by its bond length. Right? And this is an example, similar to sodium hydroxide. The oxygen-hydrogen bond in water is covalent. They don't have identical electronegativities, but they're close enough that the stable configuration that's preferred is a covalent bond. So let's look at some examples of covalent and ionic bonds. I think one of the best things that you can do in organic chemistry in general is just practice as many problems as you can. And we're going to start by drawing perhaps the simplest organic molecule, methane. Methane has 4 bonds, and they are all covalent bonds. But if you take something like sodium fluoride, let's consider them first in their elemental state. Sodium and fluorine are on opposite sides of the periodic table. Sodium is a very electropositive element, whereas fluorine is the most electronegative element. And so whenever sodium and fluorine form a bond with each other, fluorine will take on that extra electron and therefore a negative charge, and sodium, which just has an electron taken away from it, is now electron deficient. It takes on a positive charge. And so and important to note here that whenever we draw an ionic bond, we actually don't draw the line in between it like we do for covalent bonds. So something that's practical but important. And then although I don't delve into this topic in this lecture, but the reason why these atoms form an ionic bond rather than purely based on their electronegativities is the fact that they are obtaining a noble gas configuration. Okay, another example, carbon dioxide. Carbon dioxide has this structure, and this bond that I've pointed to, we would call that a double bond. But a double bond is actually made up of one sigma bond and one pi bond. We will cover what a sigma bond and a pi bond is later in this series of mini lectures. But for now, that's what that is. They're both covalent bonds because they are sharing their electrons in between the nuclei. And one more example here, ammonium chloride. Ammonium chloride has the following structure. So nitrogen, taking on 4 bonds in this case, has a positive charge. And the chloride has a negative charge. They are electrostatically attracted to each other. Again, it's tempting maybe to draw a line in between the two, but we don't do that. That's not the convention in ionic bonds. You simply place them next to each other, and it's understood that an ionic bond exists between them. In this case, that structure on the right is invalid because nitrogen has 10 electrons around it. That's 2 more than it can handle. So we've now seen a few examples of what bonds are, and particularly covalent versus ionic bonds. But let's return to that question of what is a bond. In particular, in the next mini lecture, we're going to look at where bonds reside. They reside within orbitals.